Okay, so it's called multiple comparisons. Let's take a look. And it's nice we have the value labels in here, isn't it? Where does it come up with that -3 for made contact and bumped? How does it come up with -3 there? Where's that number coming from? Right on the top of the chart, Emily.
Oh, I was just looking at...
Yep, better to look at the printout. Kind of simplified it. Where's that -3? Beverly, any thought where that -3 comes from?
It's the difference between the means.
Yeah, it's the difference between made contact and bumped. Made contact was 29, bumped was 32. That mean difference is the treatment effect, right? It's kind of like a little t-test here, a Tukey's test. It's -3. Is that difference significant? Look in the sig column. Is it significant? Is it statistically significant?
No.
No. It says probability 0.165. So the difference between made contact and bumped is not different. Let's go to the next one. How about made contact and smashed? What's the difference between those two means? (51) and 29. The difference is 22. What does the post hoc test tell you? There's a little star there.
Mean difference is significant at the 0.05 level.
There you go. It is significant. It's even significant less than that. But the post hoc test is like a t-test, but it's just more conservative. It's stopping the type 1 error. So crashed or smashed is different than made contact. How about bumped versus smashed? That's a 19-point difference. That is also significant. So in this case, you'd write out the F statement. You'd say statistically significant. In APA, what you would do, if you want to write this down, you'd write a Tukey's post hoc test. A Tukey's post hoc test indicated that smashed, the speed estimates for smashed, were significantly higher than made contact and bumped. The speed estimates for smashed, for the people who saw smashed, were significantly higher than made contact and bumped. It does everything here twice. So you just need to look at one. Is this working? Does it work? Do you understand the ideas then? Just following along. Alexis, are you all right?
Yes, that was speed estimates for smash were statistically higher than
Crashed, I'm sorry, than bumped or contacted.
contact.
Okay.
Okay.
So I have actually one more situation here, and we might actually do this. Let's see. So what I'm going to have the class do is take the data set that we have with 20, 30, 40, 25, 35, 45, and 35, 45, 55, and try to run that.
Which is part 4.
Yep, part 4. Is it working for you, Beverly?
Mm-hmm.
So let's actually start by just looking at the numbers visually here. How does that data set look compared to the previous one?
Not statistically significant.
Yeah, but if you just look at the numbers in the printout there, what's going on with the made contact group? Before, what were the numbers for made contact?
They were a lot closer.
They were a lot closer, a lot less dispersion within group. Now, 20, 30, 40. What is that doing? The mean is still pretty close to what it was before, but what is that fact that one person said 20, one person said 30, and one person in made contact said 40? That's
more dispersion.
Yeah, that's more error. Everybody in that group, even though the mean was 30, a lot of dispersion there. That's going to cause the denominator to be large. The variance within group. Same thing in bumped, right? A lot of dispersion in that group. Same thing in smashed. So the numerator here, in the previous case, what were the three means? 29, 32, and 51. What are the three means now?
30, 35, and 45.
Yeah, the means are a little less disparate, but the real problem is the variance within groups. So you ran it, and what did you get? What were the three means?
30, 35, 45.
30, 35, 45. Kind of
Okay.
different. Between groups, you had 350 sums of squares. Is that good?
A lot lower than last
It's a lot lower, but still pretty high. Variance between the groups is 175. That's good. But what's the problem?
The sum of squares within groups is
Yeah,
very high.
The sums of squares within groups is very high, but technically it's not the sums of squares within groups that technically matters. It's the variance within groups, but yet so much spread within the group, still 6 degrees of freedom. The variance within groups is now 100 instead of, what was it in the previous one? It was 3. You got a lot more dispersion within the group, so this result is what?
Not statistical.
This result is non-significant. How would you write that out? F of 2 and 6 equals
1.75.
Yep, 1.75, and then P is, oh, here's the tricky one. Beverly, you want to help?
Greater than .05.
There you go. P is greater than 0.05, non-significant. Now, if the P is greater than 0.05, would you actually even need to do the post hoc test?
No.
No, if you don't get a significant ANOVA, you don't actually have to do the post hoc test.
Yes.
And if you look at the screen with the post hoc test, because it's already done, what do you see? Is anything significant?
No.
Of course
No.
not. You can ignore the homogeneous subsets. SPSS just loves to do that. You never need that, but it does a lot of irrelevant things. So if you want to write in your notes, ignore homogeneous subsets.
Okay.
So what I'd like you to do with the example we just did, maybe write out these things on your notes, the little table, and just, what would be good to do? Yeah, actually, we'll stop the recording here. Maybe write out the table, or copy and paste the table, or I guess you could, the ANOVA table. So if you want to write out just the key numbers there, write out the sums of squares between groups, and the sums of squares within groups, degrees of freedom, mean square, F, and sig. Then what I'd like you to do in your notes is just kind of explain what all that means, how it compares to the previous example, just so you can know. And then you can write in your notes why you don't even need the post hoc test. Okay.